So we learned about the second law of thermodynamics that states that the entropy of the universe is increasing. The third law of thermodynamics states that if you're at 0 Kelvin, that means the lowest possible temperature and the molecules are not moving at all. Let's see, this might be a picture. The entropy is 0. So a perfect crystal has 0 entropy at absolute 0. So you can see here that the S only increases as you put energy into the molecules or atoms, making them move. Okay? Let's look at entropy on the molecular scale. That means we're going to zoom in. Okay? The person that described this is Ludwig Boltzmann, and this is the Boltzmann distribution as we learned before. Okay, so the temperature is a measure of the average kinetic energy of the molecules in the sample. So you can see here, you have the red is the hot, and then the green is the cold. Okay, the probability density is here, remembering that each graph underneath has the same number of particles. So if there's 5 here, there's 5 here, there's 5 molecules here. You can also see that as it gets hotter, the average speed goes up, as you can see there. But not only does it go up, the distribution gets wider. And you're wondering, why does it get wider? Okay, because when you're heating up some molecules, you're not only making it go faster, you're also making it, and that's a translational motion where they're just going from this direction to that direction in the container. Say that's a container going back and forth. That's a speed, translational motion. But they're also vibrating. Okay, so you have the vibrations of this atom going back and forth this way, and they're also rotating. So even though this guy is really slow, even when it's hot, right, 400K, I'm sorry, this is cold and the 400K is hot, even though it's slow, it still has a lot of energy because maybe it's going into the vibrational and rotational motions. Okay, so what's happening is as it gets hotter, you have more motion and more degrees of motion in terms of vibration and rotational rotation. So Boltzmann, what he did is he envisioned the motions of the sample in a particular instant in time. It's like taking a picture, okay? So for example, if you have 4 colors, 4 atoms here of different colors, that's one picture. Then you can take maybe 3 of them here and 1 there. That's another picture, and so on. All these pictures are the different ways or possibilities that 4 atoms can exist together. He called these the microstates. So the more different pictures you can take, the higher the entropy. So microstate, or the number of pictures, is really corresponds to the entropy of the system. Okay, so that's what it means on the molecular scale. So what he did is he came up with this formula, S is equal to K ln W, where K is his constant, it's just a number. S is a measure of how many microstates. That means how many pictures or how many different positions did those atoms have. Okay, so if you were able to take 1 picture, then you just plug it in there. K times natural log of 1. You get an S. If there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different positions, you put 11 right there and you can get the entropy that way. And you can see as you have more and more positions, there's more random, the S number goes up. Now you're understanding what entropy is. Okay, so let's see what happens to the entropy at absolute 0. At absolute 0, you take a picture of these molecules right here, and you only get 1 shot, because one kind of picture, because they're not moving at all. So you get 1. If you take the natural log of 1, you get 0. So therefore, you can see that entropy is equal to 0 because there is no motion, only 1 picture. As you increase the temperature, you have more and more pictures. So if you go K ln natural log of, let's say you were able to take 5 different pictures, you're going to notice that the S will go up. Okay, you multiply by K, but the S goes up. What's the natural log of 1? Let me calculate that. So this quantity here, natural log of 5, is 1.6. So it's K times 1.6. So obviously the S goes up as you put more energy into it because there are more microstates. Okay, so now let's talk about the change in entropy. So here we're only talking about S, which is the absolute number of the entropy. Here we're looking at the change. How does it change from final minus initial? I drew some molecules here. let's say in the initial one, you're only able to take, this picture. Let's say that's 1, okay? The microstate is only 1. Over here, let's say it has, you heated it up. Okay, so first it was not moving and then you heated it up. So now this molecule is able to move in a little bit closer as it vibrates. Let's say this becomes 2. Okay, so you're going to do final minus initial, and then you plug it in here and you're going to see that the entropy will go up as the microstate goes up. Okay, so that is the difference between S and delta S, the change between initial and final. Okay, here you go again. Here's the same dots. Okay, so even if you increase the temperature, you're going to get more microstates. The number of microstates and therefore the entropy tends to increase with increasing temperature. Of course, the hotter you get, the more distribution, the more vibrations and rotations. It also increases with increased number of volume. So if you have a container, let's say this one is small, you can take a certain amount of pictures. But if you increase the volume, now they have more space, they can have more areas in this volume where they can sit down and take a pose. So you have more microstates. So as volume goes up, the higher the entropy. And also the more particles there are in there, the different types of particles in there, the higher the entropy, right? Okay, the more chaos, the more people you have at a party, the more chaos, okay? So we call these the degrees of motion, different microstates. So therefore, the entropy of a gas is higher than a liquid, which is higher than a solid. Solid looks like this. Even though they're stuck in their position, they still are moving, vibrating in place, but their entropy is low. And you liquefy it, you make them able to move past each other, so the entropy goes up, right? And then you turn it into a gas, and it gets even higher. Okay. Also, when you dissolve substances, let's say this is the solute, which is a solid, and the solvent, let's say this is NaCl, each dot is an Na plus and a Cl minus, Na plus, Cl minus, and these are water molecules. They have their certain order. If this were water, there's some hydrogen bonding in there, and there's certain order. You have to disrupt those. Okay, that's why it takes energy to dissolve something, because you have to put energy into that to disrupt it. So that's why you're putting energy in. If once you dissolve it, it's becoming more chaotic. So when you turn something into solution, when you're dissolving something, the entropy will go up because it's more chaotic over here. It's very ordered over here and it's more chaotic over here. Okay? Just be careful, because sometimes if the charge is +3 versus +1, the solvation or the amount of water around this could become very ordered and the entropy may increase as well. Okay, so you have some exceptions as well, but mainly if you dissolve something, the entropy goes up. Okay? In general, the entropy increases when gas is formed, when solutions are formed, when you melt a solid, of course, when you have a number of gas molecules increases, and also if you have the number of moles increases. So here in this beaker, there's a 2 here and a 1 there. You have 3 moles of gas, 3 moles of gas. Over here, you only have 2. So does S go up or does it go down? You went from 3 to 2. One person from your party left. That means there's less chaos, so your entropy should go down because you have less. Okay, so over here, predict whether the enthalpy is positive or negative for each of the following processes. So let me give you just a reminder. Positive entropy means it became more chaotic, more random, more degrees of motion, more microstates. All those words, that just means random. Okay? Negative delta S means it's bad. It becomes more organized, more ordered. Entropy goes down. And according to the second law, this is more spontaneous. Okay, go ahead. Pause the video. Okay, here you're going from liquid to gas. More chaos. Positive delta S. Here you're going from dissolved to a solid, more organized, negative delta S. Here you're going from a solid and a gas to a solid only. So those gas molecules turn more ordered, so now you have a negative delta S here. You have all gas molecules, so you can't tell, so you have to count the moles. 1 mole plus 1 mole equals 2, 2 and 2. Then you can't tell. So choose the sample of matter that has a greater entropy in each pair. A mole of solid or a mole of gas? Of course the gas. That has greater entropy. 2 moles of gas, 1 mole of gas. 1 person at a party or 2? 2 definitely has more. Okay, 1 mole of hydrochloric acid, 1 mole of argon. So they both have a mole, but this has more atoms. So what do you think? Which is more chaotic? So maybe a family of Lozanos and a family of, I don't know, Smiths. Smiths only have 2 kids. I have 4. So there's definitely more chaos here in the Lozano household. Okay? And that's entropy.